This video is about codes and unique decodability. In common usage, the word coding often means computer programming. However, for us, the word coding is going to mean something completely different. Coding is a rule for replacing one message by another. Now, in the blocked text, we see some basic examples of this. So we have two coded versions of English sentences, and it might be fun to explain the coding rules that are used and find the original English sentences. Now, there are three main concerns in codes. The first is economy or efficiency. We want our codes to be efficient. Second, there's the concern of reliability. If I code a message and then send it through a noisy channel that alters the coded message, I would like to ideally be able to recover the original message. And then finally, there's the concern of security. Sometimes I might want to code a message that's private, and I would like that message to remain private. Now, throughout the term, we'll be discussing these three concerns, beginning with economy. So our first few chapters of the book are about economy, and that's followed by a discussion of reliability. And then toward the final days of the term, we should be able to discuss security. In order to begin talking about codes, we need some terminology. So we begin with the idea of an alphabet. So an alphabet is a finite set, which we label S. And if it helps, you can think about an alphabet as being like our ordinary alphabet, consisting of just the letters A, B, C, up through Z. So capital S in that case would be just those letters, A through Z. So the members of S, or the members of our alphabet, are called symbols. Now, if we have an alphabet, what we like to do is form words. So this set, S star, is going to be the set of all finite sequences of symbols that belong to S. And sure enough, these members of S star are called words. Sometimes they're called strings, and sometimes they're called messages. Now, in this line here, what we're saying is that words can be expressed, the collection of all words can be expressed as the collection of words of length 0, together with the collection of words of length 1, together with the collection of words of length 2, and so on. And that sort of makes sense. The only thing that seems a little bit strange here is this idea of having a collection of words of length 0. And for now, it just suffices to say that having such a collection can be convenient at times for reasons that we will see in the future. But for now, you needn't worry about it. So now here in this last bullet point, we're ready to define a code. So we start with two alphabets, S and T. And it may help to think of the alphabet S as being our ordinary alphabet where we form ordinary words, and T as being sort of a substitute alphabet where we're going to create our coded messages. So a code, C, for S using T is a function, a one-to-one function that eats elements of S, that is, it takes symbols in S and spits out strings in T star. So if S, little s, is a symbol in capital S, then C of S in T star is called a code word for S. Now the set capital C, which is the collection of all images, C of S, that's the set of all these code words. That is also referred to as the code. So when we talk about a code, we're either talking about this function from, say, our ordinary alphabet into strings on a different alphabet, or we're talking about these collections of code words. Here we explore a few questions that will help us firm up our knowledge of the terminology that we discussed on the previous slide. So in the first question, we have our ordinary alphabet, capital A, and capital B, on the other hand, is just going to be the collection of symbols 0 and 1. So we're going to define a function C from A to strings on B as follows. So C will take vowels to the symbol 0, and C will take consonants to the symbol 1. The question is this a code? Now remember that a code must be one-to-one on the domain alphabet. That is, this function C must be one-to-one in order for it to be a code. And unfortunately, this function is not one-to-one, right? Because there are two distinct elements in the domain, for instance, A and E, which are both vowels, that get sent to the same element in the codomain. So this function is not one-to-one, and therefore C is not a code. Okay, in the next question, well, we have our alphabet S consisting of the three letters X, Y, and Z, and we're going to define another function C from S into B star, where B again consists of the symbols 0 and 1. And we're going to let it be defined by C of X equaling 0, C of Y equals the string 1, 0, and C of Z is the string 0, 1. So is this C a code? And if so, what are the code words? What's the length of the longest code word? What's the length of the shortest code word? Now here, this C is in fact a code. It's a one-to-one function, right? X, Y, and Z are all sent to distinct things, right? So it satisfies being one-to-one. Now, the code words from the previous slide, those are the images of the alphabet elements X, Y, and Z. So the code words are just 0, 1, 0, and 0, 1. So what's the length of the longest code word? Well, we have one code word of length 1, and we have two code words of length 2. So apparently 2 is the length of the longest code word, and the shortest code word has length 1. So now we move on to part C, where we're looking at the very same code that was described in part B, and the question is the string 100 a code word? And the answer is no, because remember, a code word is the image of a single element of the domain alphabet. So here the domain alphabet is just X, Y, and Z. It's not combinations of X's and Y's and Z's. It's just X, Y, and Z. X gets sent to 0. Y gets sent to 1, 0. Z gets sent to 0, 1. So those three strings, 0, 1, 0, 0, 1, are our only code words. So this thing is not a code word for the reasons we just talked about. Now, let's suppose we wanted to use the code from part B to sort of encode a message that isn't just X or just Y or just Z. So in part D, we're asking, well, how would you encode the message XYZ? And the only thing that makes sense would be to first encode X, then encode Y, then encode Z, and then put the resulting strings together. So if we encode X, we get 0. Right, that's from up here. If we encode Y, we get 1, 0. And if we encode Z, we get 0, 1. So this is how a reasonable person using the code from part B would encode the message XYZ. Right, so the reverse process is important to us, right? If someone drives up and hands us this string 01, 001, it would be nice if we could go and reconstruct the original message XYZ. So can we do that here, right? Part E says, are there any other messages in S star that when encoded give the same result as encoding the message XYZ? So if you look at this string 01001, you could see that that's the same as ZXZ. Right, if you encode ZXZ, remember Z encodes as 0, 1, X encodes as 0, and Z encodes again as 0, 1. That's the same string we had up in part D. So we should be left with the impression that while the code of part B is a code, it is somehow not very useful because it doesn't, if you are given some sort of string in the alphabet B star, you don't necessarily know what message in S it came from. On this slide, we clean up a few loose ends from the previous slide. So first, we discussed at some length a code on the previous slide with alphabet S as our domain, and the strings B star as the codomain, where B consists of just the symbols 0 and 1. So any code like that, where the outputs are binary strings, that is, strings consisting of zeros and ones, a code like that is called a binary code. And we're going to talk a lot this semester about binary codes. Second bullet point discusses this sort of natural way to encode words formed from the alphabet S. So if we have a code, we can extend this code to not just symbols in S, but words or strings on S by doing really the only thing that makes sense, right? If I want to encode a word, I'm just going to encode each symbol in S individually. Now, in the final bullet point, we have a new definition. So we say that a code, C, from S to T star, is uniquely decodable if the extended function that we talked about up here in the second bullet point is also one-to-one. Okay, unique decodability is a really important property because what it says is that if I start with some string over here in T star, and I know that it came from something in S star, then it can only have come from one thing in S star. That is, if I'm given a string in T star that comes from a coded message, I am able to reconstruct with certainty what the original message was back in S star. Now, you might remember on the previous slide, we had a code that did not possess that property. Remember, we had two messages in S star, namely XYZ and ZXZ, that were sent to the very, very same string in T star, which on the previous slide, it was B star, right? So that code on the previous slide was not uniquely decodable. So unique decodability, it is vital because it allows us to reconstruct with certainty original messages from coded messages. So apparently unique decodability is an important feature for a code to have. Unfortunately, if you just try to check unique decodability using the definition on the previous slide, it can be quite difficult. So an important question is, what sort of easy to check conditions does a code have that would ensure that it's uniquely decodable? So I'd like to leave you with a couple of questions that you should think about. So first, in part A, we have our alphabet S, which is just, again, the letters X, Y, Z, and we define a code, C, from S into B star. So this is a binary code that will send X to 0, 0, Y to 1, 0, and Z to 0, 1. So first of all, this is indeed a code because the function C is 1 to 1. Now, is the code uniquely decodable? So see if you can see why or why not that's true. Now in question B, let's suppose we have just a code C from S to T star, and it has the property that every code word has the same length, right? Like in part A, every code word was of length 2. Let's suppose we have a code where every code word is of length n. Do you think the code is going to be uniquely decodable? So I want you to try to play with some examples. And if you think the answer is yes, then try to prove it.